Okay, so during the previous session we have started the exercise 5 of the list 5. Okay, we are going to start with this one. Okay, so before the break I will do exercises. Okay, and then I will continue the last little part that concerns the midterm exam, the one concerning moment generating function. Okay, so we have already done the question 1 together during the previous session, okay? And we have remarked that if I define gamma of alpha this way, the integral between 0 plus infinity exponential minus y alpha minus 1 dy. So this is the integral of a positive mapping that is finite. In fact, if I impose a condition on alpha, and the condition we have seen together is that alpha has to be strictly greater than 0. Okay? So gamma of alpha is finite. Alpha is strictly positive. It means that I have the right to consider this integral when alpha is strictly positive. Okay, I have finished with this part, okay, during the previous session. Okay? Clear for everybody? So I have to continue. The objective of this exercise will be to deal with the gamma distribution, okay, that we are going to build from this mapping here. And that will be something that will extend some distribution we have already seen together in class. Okay? So question 2 is a very basic one. Prove that gamma of 1 is equal to 1. So first I remark that 1 fulfills my condition. 1 is strictly greater than 0, so I have the right to consider gamma of 1, and it will be a number. Okay, and I want to prove here that this number is none other than 1. So if alpha equal to 1, I obtain what? I simply the exponential part. What is this integral? You have the answer. Can you give me an argument? So you can do the computation because the mapping you have inside as a primitive, I know, but
it's lambda equals 1 for an exponential.
Yeah. So I can use what I know from the course, and I see that here it's just the integral of the density of an exponential of parameter 1. So this integral is necessarily equal to 1. Okay? So if it's possible, I prefer not to compute, but just use what I know from the course. Okay? And you will see that today I will use a lot of things we know from the course, okay, in order to do my computations. So I can say that here I can write this way. It's the integral between minus infinity and plus infinity of, I write it this way, the density of an exponential of parameter 1. Okay? And I know by definition that the integral of a density function is equal to 1. Okay? So it's the integral of the density of an exponential of parameter 1. That's why this integral is simply equal to 1. Okay? So here it's very basic. If you want not to use this result, okay, just compute the primitive of exponential minus y, that is just minus exponential minus 1, and compute the integral. But here, it's not necessary, okay, to use the primitive. I can simply use what I know from the course. Okay? So nothing to say with this question. Gamma of 1 is equal to 1. Third question. There are two questions in the question 3. First, I want you to prove that for all alpha strictly positive, in fact, there exists a relation between gamma of alpha plus 1 and gamma of alpha, that is the following one. Gamma of alpha plus 1 is equal to alpha gamma of alpha. Okay? just keep in mind that here everything is well defined because I impose alphas to be strictly positive. It implies that gamma of alpha is okay, and also gamma of alpha plus 1, because if alpha is strictly positive, alpha plus 1 is also strictly positive. So all the terms will be numbers. Okay? Okay.
So just one question. On the exam, we would have to write it that alpha plus 1 and alpha strictly wouldn't do that, okay?
Right, better. I repeat, when I correct an exercise, I speak. You won't have the possibility to speak, so give me the best you can, okay? And typically here, I have done the job in question 1 to be sure that I will be able to compute the integrals involved in the exercise, okay? So alpha strictly positive, alpha plus 1 strictly positive, so gamma of alpha and gamma of alpha plus 1 well defined. So you will have a dilemma that is to write all you know, okay? But I prefer you to write concise things that are very precise, okay? It will help me to correct, okay? For me, the best is a very small copy with everything inside, okay? Okay. So do you have an idea to do this? So, if I have a look on what is gamma alpha and gamma alpha plus 1, the only thing that is changing is the power in the y here, okay? So I have gamma of alpha, that is this one. And gamma of alpha plus 1, that is equal to this simply, okay? I plug inside alpha plus 1. So I need to make a connection between this one and this one, okay? First question, is it possible to prove this kind of relation by induction? Is it a good idea to try to do by induction? I have a yes, I have a no, I have a maybe here. No, it's not a good idea to try to do an induction. Why? Because when you want to prove something by induction, okay, you want to prove a property that is indexed by the integers. Okay? So you will prove it for n equal to 0, then suppose that it is true for n, and then prove it for n plus 1. Okay? And then you will prove it for any n. Here, my alpha is a strictly positive real number. Okay? If you do an induction, you won't prove what you want, because you have to prove that it is true for any strictly positive real number. Something that is not in the framework of an induction reasoning. Okay? So typically, if you have a look on the question here, I have something to prove for all alpha strictly positive, and then to deduce something for all n. Here, it should be possible to do an induction, because I have to prove something that is indexed by a subset of the integers here. So an induction is possible. It's not necessary to do an induction, but it's possible to do here, not here. Okay? So I have to do it directly. Okay. In general, when you have relations to prove between mappings that are defined as integrals, there is a tool that you can use. Which one? I see that this one and this one are not very far. Okay? The only thing that is changed is the power here in the expression. How to pass from this one to this one? If I have y to the power alpha, how it is possible to obtain y to the power alpha minus 1? Computing the derivative. So in fact, what we are going to do is an integration by part formula in order to do this. Because the idea, if I start from this one, the idea is to use an integration by part in order to transform this one into this one up to a constant, but whatever, okay? And here it will be very easy to find the primitive of this one. So I am typically in the situation where we are going to apply an integration by part formula with this one, that is the one I want to compute the derivative, and this one, that is the one I want to integrate, okay? So I use my integration by part formula. And if I use my integration by part formula, so I can say the following: gamma of alpha plus 1 is equal to what? It is minus the integral between 0 and plus infinity. I will write it this way: j f prime dy plus f j between 0 and plus infinity. The integration by part formula, the classical one. Okay. But I know j. What is j here? If j prime is equal to exponential of minus 1, j of y is just minus exponential of minus y. And then f prime of y is just equal to alpha y alpha minus 1. Okay? And so I have just to plug inside my integration by part formula f, j, f prime, and j prime. So I obtain what? So j is minus exponential minus y. F prime is equal to alpha y alpha minus 1. So I obtain plus integral between 0 and plus infinity of exponential minus y, alpha y alpha minus 1 dy. And then I have to take the product f times j between 0 and plus infinity. At 0, I obtain what? So I have done a little mistake here. Oh, it's okay, it's human. So what I obtained for the term here, so I have this one here. Okay, so f is y to the power alpha. So if I take alpha being strictly positive, so if I take this one at 0, I obtain 0. And if I take the limit of j in plus infinity, 0. So here, okay, I am interested in f times j taken between plus infinity and 0. In plus infinity, I have the exponential that give me a limit equal to 0. And at 0, I have the y to the power alpha that give me 0. So I obtain 0 here. And I have exactly what I want to prove. Because what I have proved on the board here, that gamma of alpha plus 1 is equal to what? Is equal to alpha multiplied by an integral that is none other than gamma of alpha. So here you have alpha gamma of alpha. Okay? And the idea here is just to use the basic integration by part, because here I have a power alpha. In what I want to obtain, I have a power alpha minus 1. So the idea is to compute the derivative of it, of this one, to make appear this part, okay? And in order to do this correctly, I use an integration by part. Okay? Clear? So you have the relation I want to prove in the question 3. Okay, that gamma of alpha plus 1 is equal to alpha gamma of alpha. Okay? So in the second part of the question, I want to deduce from this one what is the value of gamma for the integers. So I want to prove that for all n belonging to n star, I want to prove that gamma of n is equal to n minus 1 factorial. So it is one of the nice property of the gamma function, that is, with a shift it coincides with the factorial. Okay? So you have gamma of n that is equal to n minus 1 factorial for any n belonging to n star. Okay, so I can imagine that we are going to use what we have proved previously because there is a deduce here. Okay? So I can do it directly, it's possible, okay, but if I want to do it very properly, here I can use an induction. Because I have a property to prove for all n belonging to n star, okay, doing an induction reasoning can help us to do this in a clear way. So by induction. So what is the first step of my induction? I have to see what happened for n equal to 1, because n belongs to n star, okay? So for n equal to 1, what happened? I have already done the job for n equal to 1, because I know what is gamma of 1 from the previous question. So gamma of 1 is equal to 1, and I know that 1 is also equal to 0 factorial by definition. Okay? So I have what I want for n equal to 1. Now, so I have initialized my induction. Now I have to prove the heredity. So we are going to suppose the property true for n, and we are going to prove it for n plus 1. So suppose that gamma of n is equal to n minus 1 factorial. Okay, so I suppose it for n, and my job is to prove it for n plus 1. Okay, and of course we are going to use our hypothesis, that is that gamma of n is equal to n minus 1 factorial, and my job is to prove that gamma of n plus 1 is equal to n factorial. As usual, when I have to do an induction, I have to make the link between what I want and what I know. What will be the link between gamma n plus 1 and gamma n? It will be given by what I have proved previously. If I use the previous relation, plugging alpha equal to n, I know that gamma of n plus 1 is equal to n times gamma of n, and it's finished. So I have this one, according to the relation I have proved here. And by induction hypothesis, I know that gamma of n is equal to n minus 1 factorial. And n times n minus 1 factorial is equal to n factorial by definition. Okay? So you can do it directly, it's possible, okay? But here with this little induction reasoning, okay? And here, the main step is this one that was in the beginning of the question. Okay? So we have proved that this mapping defined as an integral coincides with a little shift with the factorial mapping for the integers. Okay? And in fact, it's an example, in fact, the only case where you will have a mapping that is very regular and that coincides with, okay, the factorial map. Okay, with this, so basic induction, very short, okay. having in mind what I have proved at the beginning of the question. Do you have some question concerning this? So just here, keep in mind that, I repeat, when you have a mapping that is defined as an integral, okay, if you want a relation involving two of such mapping, integration by part is not a bad idea to have in mind, okay? Questions? No? So now we are going to define the gamma distribution. It's the question 4. So I erase this part here. So I keep just what I will use, that is the definition of gamma here, this way. May I erase this part of the board? Okay, so I define something that we are going to prove to be a density function. And from now on, it will be an expression that you will need to know. Okay. For lambda strictly positive and alpha strictly positive, we define f this way. So f of x is defined as lambda to the power of alpha x alpha minus 1 exponential minus lambda x over gamma of alpha, indicator function that x is strictly positive. Okay? That's exactly what I have written at the beginning of the question 4. I have this. And what is the question I have to answer? First, I prove that f is a density function. Okay? I have to prove that f is a density function. So what is the definition of a density function? So if I know my course, and I will have 2 for the midterm, okay? It's the definition 16. The density function is this one. Something that is positive in the large sense, continuous except for a finite number of points, and with an integral equal to 1. Okay, so I have 3 things to check if I want to prove that something is a density function. So concerning the positivity here, what can I say? Nothing, because my lambda is positive, so this term is positive, x is strictly positive, exponential is always positive, and my gamma is the integral of a positive thing, so everything is positive. So for the positivity, nothing to say, because it's just the product of terms that are positive. So it's not always strictly positive because I have an indicator function, but it's not what I have to prove in the definition. Okay? In fact, here it's strictly positive on r plus star and 0 otherwise, but whatever. Okay. Concerning the continuity. In fact, there is only one point that may be a problem. Which one here? Which point may be a problem for the continuity? 0. But I don't mind about 0. Because here, so for x negative in the large sense, this is equal to 0. So something that is continuous. Okay? If I am strictly positive, I have this relation here. And for x that is strictly positive, here you have just the product of mappings, these two that are continuous. So you have something that is continuous. So maybe you have a point of discontinuity at x equal to 0, but you don't mind, because you don't mind about finite number of points. Okay? So f is positive for sure. F is continuous on R, maybe except 0, but I don't mind. Okay? About 0, and I don't have to check if it is continuous or not at 0. I don't mind. Okay? because the only thing I want to prove is that it is continuous except for a number of points that is not too big, and in my definition, a finite number of points. So C0 means continuous. Okay. On R except 0, because maybe I have a problem at 0, but whatever. Okay, I don't have to spend time on it, because in the definition of my density function, I just have to check that I am continuous except for a finite number of points. Okay? Repeat that for x negative, I am always 0, so I am continuous. For x strictly positive, I have this expression involving just, okay, mappings that are continuous on R plus star here. Okay? Exponential is continuous everywhere, and this one, maybe it is not continuous at 0, but it's not what interests me. Okay, 0. So in fact, in this particular situation, okay, the main point is just to prove that the integral is 1. Okay? And in order to prove that the integral is 1, we are going to use what we have done previously concerning the gamma function. Okay? So I am interested now in the integral of this one. So I have an indicator function, which is something that is defined from 0 to plus infinity. Okay, of what? Lambda alpha x alpha minus 1 exponential minus lambda x over gamma of alpha dx. And my job is to prove that this integral is 1. Okay? And of course, I repeat that we are going to use the definition of gamma that is given by this expression we have worked with before. Okay? So, in fact, I have the integral of this term to compute. Okay? And if you have understood, I have to prove that the integral of this term is just equal to gamma of alpha, because I want that the integral of this term is equal to 1. So I have to make the link between this expression here and this one here. I see that the main difference between the two is the fact that I have a lambda in the exponential I don't have here. Okay? So in some sense, I want to make this lambda disappear in my integral in order to be able to come back to the previous integral. Okay? I repeat. I want to prove that this one is 1. To prove that this one is 1, we are going to prove that this one is equal to gamma of alpha. And then at the end, I will have 1. Okay? So in fact, I want to prove that the integral of this expression is equal to this integral here. So it's not exactly the same expression here and here. But I remark that they are not too far. I have exponential, I have power, okay? And the main difference is that in the exponential here, I have just minus y. Here I have minus lambda x, okay? What can I do? So for the moment, it's not a problem of probability. Huh? We just do integrals here. It's an exercise about integrals.
You can take out gamma and lambda to alpha out of the integral.
Yes, and why not? It's possible to do this. But it will change nothing. Huh? Typically, you will have to compute the integral of this one. Okay?
To take right equal to the lambda x and change x into change lambda x into y.
Huh?
You can use that.
The idea is that, okay, I want to make this lambda disappear here. Okay? I can try to do a change of variable, in fact, in order to come back to what I have here. Okay? I'm agree with you that a good idea here is to define, so we do a change of variable. And my change of variable will be y equal to lambda x. It's a very, very basic change of variable because it is a linear one. Okay? So you can't do simple. Okay? It's simpler. So let's do. So first, my bounds. My lambda is strictly positive. So when x is 0, y will be 0 for sure. And when x will go to plus infinity, y will also go toward plus infinity because my lambda here is strictly positive. So I don't change, okay, the bounds in the integral. So I have plus infinity here. So then what I have? Well, the lambda to the power alpha doesn't change because I just changed the variable. The gamma of alpha doesn't change. I have x to the power alpha minus 1 that will become y over lambda to the power alpha minus 1. I have exponential minus lambda x that will become exponential minus y. And the gx that will be equal to y. To what? Excuse me? I have dy here. That is lambda dx. Okay? So my dx is equal to dy over lambda. So it's a change of variable, something that is considered as a prerequisite in this course. If I remind in the document I have written concerning change of variable, you have exactly this one inside. Okay? And now, what can I do? I can simplify a little. I have lambda to the power alpha, and then I divide by lambda, and I divide also by lambda to the power alpha minus 1. And in fact, I have a simplification between all the lambda. And at the end, I obtain what? The integral between 0 and plus infinity y alpha minus 1 exponential minus y dy over gamma of alpha. But by definition of gamma of alpha, I have just something that is equal to 1. Okay? So I have proved that I have a density function, proving that I have something that is positive, continuous except maybe at 0, but I don't mind, and with an integral equal to 1. Okay? And from now on, and it's something that is supposed to be known for the midterm exam, I will say that x follows. So be careful concerning the definition. The definition I will use for the gamma will be this one. Depending on textbooks, you may have inversion of the parameters. The one I will use is this one. It's the one I want you to use. Okay? So we say that gamma, x follows the gamma of parameter lambda, alpha lambda. Okay? With alpha strictly positive and lambda strictly positive, if the density function of x is given by this expression. So it's a new density that is considered as a density from the course. Okay? So this is the gamma distribution of parameter lambda, alpha and lambda being strictly positive. Okay? So now we are going to study a little this distribution. But first, we are going to see that in fact, this distribution we have already seen together some special cases. Okay? Typically, we have already seen together the exponential, that will be a subcase of this one, and also the chi-square distribution. You remind in the course, starting from n01, we have computed together the density of the square of n01 that I have called the chi-square of parameter 1, okay? we are going to prove that in fact this chi-square is just a particular example of a gamma distribution. We are also going to compute its expectation and its variance, and we have nice formula in terms of the parameters for the expectation and the variance. Okay, and I will introduce the definition of the extension of the chi-square we have already seen together. The definition that will be used in the statistical part. Okay. So this exercise is important because it's result that we are going to use later on, in particular in the statistical. Okay, so first of all, it's the question 5. I am interested in the gamma of parameter 1 and lambda. You just have to check that in fact this distribution is none other than the exponential of parameter lambda. What I have to do here, I have the density of a gamma of parameter alpha lambda. I want to see what happens for a gamma 1 lambda. So in this case, what is the density of x if alpha is equal to 1? If alpha is equal to 1, I have lambda to the power alpha, that becomes lambda. I have x to the power 1 minus 1 that disappear. I have exponential minus lambda x, indicator function of x strictly positive. And below I have gamma of 1. And what is gamma of 1? 1. Okay, so it's finished. And here you see exactly the density function of an exponential of parameter lambda. Okay? So I recognize that taking alpha equal to 1, I recover the density function of an exponential of parameter lambda. Okay. So typically, what is the expectation of a gamma 1 lambda? No, 1 over lambda. What is the variance of a gamma of parameter 1 lambda? Okay. You have the answers here. Okay. That is this. For alpha equal to 1, I recover, of course, okay, the things concerning. Okay. So I have seen a particular subcase of the gamma, and the first particular subcase is the exponential of parameter lambda. Okay. So I will do for the moment, okay, so I erase nothing, I will erase this one here. I keep the definition on the board. I have done the job for the gamma 1 lambda. And now, in the question 6, we are interested in gamma of 1/2. Okay? It's what I am interested in. And I have to prove that the density of this gamma will be exactly what we have done together in class. That is, we will obtain the density of the square of n01 that I have defined in the course as the chi-square distribution of parameter 1. But first of all, before to recognize, okay, that what I have here is exactly what we have seen together, let's have a look on what is this density function. And at the end, we are going just to compare the density function we are going to obtain and the one we have computed together in class, that is the one of the square of n01. So what is the density of a gamma 1/2, 1/2? I have to plug inside what is 1/2, 1/2 inside. So the density is given by what? Lambda is 1/2, alpha is 1/2. So I have this way, the square root of 1/2. Then I have x to the power 1/2 minus 1, that is this one here. Okay? Exponential minus x over 2, because lambda is equal to 1/2. Indicator function of x strictly positive. Okay? And I have to divide by gamma of 1 half. So, if I write this is equal to what? 1 over the square root of 2x exponential minus x over 2 over gamma of 1 half indicator function of x strictly positive. So for the moment I have just plug, okay? But here I see that if I want to continue my computation, I have one term that I have to compute. Which one? This one. Gamma of 1 half. Okay? I have to compute it because keep in mind what I know from for the moment. Okay, for the moment, and from the previous question, we have seen together that what is gamma of n? Okay, for n belonging to n star. But I have nothing about gamma of 1 half. So I have to compute it in order to see what is, okay, concretely this density function. Okay. So my job now is to compute gamma of 1 half. What is gamma of 1 half? I just plug, it is integral between 0 and plus infinity of exponential minus y over the square root of y dy. It's what I want to compute. So, there are two possibilities here in order to give you an hint in order to do this. First possibility, you know your course. That is, you have seen together, we have seen together in class, what is the density of the square of n01. You know it, so it means that you will know exactly what you need to obtain in order to cope with what we want. Do you remind what is the density of the chi-square in the course? So it is not in the slide, but it's the computation we have done together. It's the computation we have done just after this proposition, okay? It was this here, not this one, but this one here. Yes, it was typically just after this, excuse me, well, yes, the two examples here. We have done the job. And what is the tool we have used here? We have computed the distribution function, and then in order to obtain the density, compute the derivative of the distribution function. So do you remind what we have obtained for the question 1 here, in the slide 9? Maybe no, huh? The midterm is not today, so... Nobody? So you have it in the...
Exponent minus x divided by the square root of 2xy.
You are not very far.
And this function, x plus.
You are not very far. So it was, I am agree with the beginning. This one. It was exponential minus x over 2. It was the chi-square, this one. The density of a chi-square in the course was given by this expression. 1 over the square root of 2 pi x exponential minus x over 2, indicator function of x strictly positive. Okay? So, if you see what we have and what I want, we are not very far. I am just missing the 1 over the square root of pi. That is in fact that I have to prove that gamma of 1/2 is equal to the square root of pi. Okay? So it's better to know, because if I know exactly what I will need to obtain. Okay? So there are two possibilities. You have a good training about integrals, and so you are able to compute this one, because it's a basic integral to compute. Or you know the course of probability, you know exactly what you have to prove, and so you deduce what you need to obtain for this one. So my job will be to prove that this one is equal to, in fact, the square root of pi. Okay? Because if I prove this, I will prove that the density of a gamma 1/2 is exactly the density of my chi-square of parameter 1. Okay? This is the square of a n01 we have computed together. Okay? So it's what I have to do. Once again, I am fluent with integral, it won't be that complicated, or I am not that fluent, but I know my course of probability. Where in the course of probability you have something with pi inside? The Gaussian. Okay? It's maybe the only place where I have pi inside in my course for the moment. Okay? So I have a pi here. So a priori, when I see this and this, okay, it's not that close to, okay? In fact, I am not very far from this. So keep in mind that if you know the definition of a Gaussian distribution of parameter n and sigma square, it means that you are able to integrate a lot of mappings. Because it means that you know that the integral of the Gaussian density is 1. So you know from the definition of nm sigma square that if you compute this, okay, I ask you to compute this integral, you know what is the value. The value will be the square root of 2 pi sigma square. By the fact that the integral of the expression in blue is 1. Okay? From minus infinity to plus infinity. So the integral of the negative exponential is equal to the square root of 2 pi sigma square by definition of the fact that I have a density function here. Okay? And I compute nothing. Okay, I compute nothing. Okay. So we need to have an idea in order to use what I know for what I want. So here I see a main difference between the two. The first main difference is that inside the exponential here, I don't have a square. Here I have a negative square. I have just minus 1 here. So what can I do? I change the variable. I make the square appear and see what happens. It's not a bad idea because I know things about integral of exponential minus of squares. Okay? So let's try to make appear squares and see what happens. And you will see that if we do the job, okay, it will be not that complicated. So in the integral I am interested in, that is this one. I do a change of variable, that is z equal to y squared. Why this is a change of variable here? Be careful, huh? Change of variable has to be something that is bijective. And a priori, the square mapping is not bijective on R. But I am on R plus here, so it means that I am only on this part where the square is bijective with a bijection that is the square root. Okay? So it's really a change of variable. mapping that is bijective here. That is here, simply continuous and strictly increasing mapping from R plus into R plus. Okay? I can try to do my change of variable now. I apply the change of variable formula. I will continue here. I erase this one. Mind that my job is to prove that gamma of 1/2 is this one. That's what I do here. So, okay, so when y is 0, z will be 0, and when y goes to plus infinity, z will also go to plus infinity. So I don't change the bounds of my integrals. Okay, exponential minus y becomes exponential minus, is it what I want to do here? It's not what I want to do here. No, because if I do this, I will make appear a square root, so it's this one that I want to do. Okay?
But it's over 2. Yeah?
It is over 2.
Yeah, over 2. So,
No, here it's over 2?
yeah, because it is minor s squared over 2.
No. It's gamma of 1/2 I want to compute.
Oh, yeah.
Okay? In gamma of 1/2, come back to the definition. Gamma of 1/2 is this one here. You don't have over 2 in the exponential. You have over 2 in what I have erased here. So keep in mind what I have done. Listen to me. No, I know what you have in mind. You do a mistake. So here, I am interested in what happened in this one when I take alpha equal to 1/2 and lambda equal to 1/2. So I am agree with you that when I do the job for this exponential here, I will have exponential minus x over 2. But what I will need to compute will be this term, that is gamma of 1/2. Gamma of 1/2 is given by this expression where I don't have, okay, I don't have an over 2 in the exponential here. Okay? So it's this one that I want to compute, gamma of 1/2. Okay? If I do my change of variable this way, in order to make a square appear here, okay? What is not okay with you? I think that you have a problem.
And just because I'm told the y is equal to the s squared over 2.
Well, if you want, okay, I do this one, basic one. I want to make appear, you can do this if you want, okay? It's possible to put over 2.
Yeah, it is very close to the formula of,
For this one?
Yeah.
Yeah, I'm agree. Yeah, you can do this. I will do only this one. Because if I take sigma square equal to 1/2 here, it makes disappear the 2, okay? So it's what I will do after. You can do directly over 2 if you prefer, why not? It's okay. It's not what I will do, but you can do this one, okay? But just the basic one, the square, okay? Without any constant. So if I do this, I have for the exponential by exactly what I want, that is exponential minus z squared, okay? So what is 1 over the square root of y? 1 over the square root of y will be 1 over the square root of z squared. What is this one? So a priori it's 1 over the absolute value of z, but z is positive. Okay? So 1 over the square root of y is just 1 over z. Okay? Because z is positive, so the absolute value of z is just z itself. Be careful, huh? The square root of the square is not equal to z. If you take z equal to -1, it doesn't work. But here I don't have problem because I work with positive numbers. Okay? I integrate from 0 to plus infinity. Okay? And it remains the dy. And what is dy? Dy is equal to 2z dz. Okay? Z being equal to the square root of y. Okay, so I can just plug in fact here dy is just 2z easy. Of course I can simplify. That's why I've done the job. I have simplification between this. And now, what I have to compute, I have just to compute 2 times the integral between 0 and plus infinity of exponential minus z squared dz. Something that is a priori a little bit simpler to express than this one here with the square root. Okay? So are you okay with what I have done? So the idea, okay, to make you clear about how I think is that if I know the expression in blue, I know exactly what I have to find for gamma of 1/2. Something that is in relation with pi. In my course, I have integrals that are in relation with pi, the one related to the Gaussian density function. So I have this in mind. And you will see that I will use this one a lot in this course in order to compute integrals without doing explicitly the computation, but just using what I know. Okay? So I see that here I have a square inside the negative exponential. That's why it's not that natural to make this change of variable. I want to make the square appear in the exponential in order to try to come back to what I know. Okay? So now, what can I say? If I have a look on what I know, it's not an integral over 0 plus infinity, but it's an integral from minus infinity to plus infinity. But what can I say here? But exponential minus z squared is a mapping that is symmetric with respect to, okay? So you have here, so at 0, 0, it's 1, excuse me, and then I have something like this, okay? Okay? So I have an even mapping. In particular, if I try to compute the integral from 0 plus to plus infinity, it is the same thing as the integral from minus infinity to 0. So 2 times the integral from 0 to plus infinity here. So 2 times this part is just the whole integral here. So this is using the symmetry. I have this one. 2 times the integral over 0 plus infinity is in fact the integral from minus infinity to plus infinity, using the symmetry of the mapping. Okay? Because what I have inside here is symmetry, so I can remove the 2, considering the integral from minus infinity to plus infinity according to the picture I have done. And now it's not very far from what I want. Okay. So how to compute this one? From what I know here. But I want just exponential minus z squared. So I have to take what as a parameter here? First m equal to 0 in order to make disappear the minus m here. And I have to take sigma squared in order to remove the 2. So I can take sigma squared equal to 1/2. So if I take m equal to 0 in this expression and sigma squared equal to 1/2, I obtain square root of pi. That is exactly what I want to prove. Okay? So you see the principle here. The principle here is to try to use what I know. Okay? That is to come back to the density of a Gaussian, because I know that I have, from the definition of the density of a Gaussian distribution, this equality that is true for any m and any sigma square. Okay, so playing on the m and the sigma square, you are able to compute a lot of integrals. Okay, typically this one. Okay. So I have done the job. Because if I plug, so if you have some question, ask me. It's the last week before the holidays. Okay, so do you have a question? You have a question? No? You have a question? So be quiet if you don't have a question. Okay. So ask questions. It's your job to ask questions. Mine is to answer. Okay. So it's okay? So change of variable. If I don't think why I do the change of variable, my idea is that I have a square root of pi to obtain, and I want to make the link with Gaussian density function. Okay? So it's something that I want you to keep in mind in the course. Okay? So I have gamma of 1/2 that is square root of pi, and if I plug inside the density of a gamma 1/2, I recover exactly what I have in blue here, that was defined in the course as the density function of a chi-square of parameter 1. Okay? So you see nothing with the blue, yes? Okay? Okay, so I have a second subcase of the gamma, that is the chi-square of parameter 1. Okay? Chi-square of parameter 1 is just a gamma 1/2. So typically, in a few minutes, we are going to be able to know what is the expectation and the variance of a gamma. So we'll be able to say what is the expectation and the variance of a chi-square. Okay. Question? Okay? So I want you to be able to do this for the midterm. But don't worry, the midterm is in, let's say, 20 days. You have time, okay? Yeah, 10 of November, okay? Got the break, okay? Holidays. So for my home, I have bought a big whiteboard. So I will be able to organize a Zoom session with you during the holidays, and I will be able to answer using my beautiful whiteboard, okay? I hope that I will just save it on Friday. Okay, it's not bigger than this one, but not that twice this one, so it's a big one. Maybe this one. So I will be able, even if we are not able to come to the university, I will be able to do the course. Okay, from my room. Okay, and maybe from my bed. Because I have also bought an iPad Pro. Okay, so I will be able to do everything. Okay? So you will have class until the end, for sure. Okay? All the sessions, all the exercise. Okay. So I have this. Okay, so I continue. And now my job is to compute the expectation. So we have done question 6 to compute the expectation and the variance of a gamma. Okay. So I erase everything. And you will see that it will take one line to do this. Because I won't have to do the computation, because in fact it's something that I already know from the previous questions. But let's remind what is the definition of the gamma density. So in general, in the course, I have said to you that in the case of continuous random variable, I know that the integral of the density is 1. In order to compute the expectation and the variance, sometimes, it's necessary or interesting to do integration by parts to compute expectation and variance. It's what I have done in the case of the exponential, for example. So for the Gaussian, it's not what I have done, but maybe I have done it for the variance, okay? But here, typically, it won't be necessary for me to do this because of the following. So, it's the question 7, maybe, yeah? So, I have my gamma alpha lambda, this way. And the density is given by what I have on the top. So, integral 0 plus infinity of lambda alpha x alpha minus 1 exponential minus lambda x dx over gamma of alpha. I know that this one is equal to 1. Okay? So it means that if you know the definition of a gamma, you are now able to compute a lot of integrals. The one with a negative exponential and before a polynomial in x, let's say, or something like this. Okay, so I am interested in the expectation and the variance. Okay, so if it exists, the expectation of x is what? It is defined in the continuous case as the integral between minus infinity and plus infinity of x times the density function of x. Okay? It's what I have to compute. So let's replace by the density function and see what happens. So if I replace inside, I have minus infinity. Yes, I have so. Since I have an indicator function in the density function, it will be an integral from 0 to plus infinity of x lambda alpha x alpha minus 1 exponential minus lambda x over gamma of alpha dx. But I can simplify a little here. What can I simplify? By the x. And the integral I am interested in is just lambda to the power alpha x alpha exponential minus lambda x over gamma of alpha dx. I have this to compute. And what is interesting with the gamma density function is that you see that the integral I want to compute is what? So I have constants, whatever the constant, but I have integral of what? X to the power something and a negative exponential, something that I have exactly here. Exactly. It has the same form as what I know. So if I start from this one, okay, as I have done in the Gaussian case, I can also say that I know what is this. You are able to compute these integrals and to know what are their values. Their values are equal to what? It's gamma of alpha over lambda to the power alpha. Because this integral is 1. So the integral of this one is gamma of alpha over lambda to the power alpha, necessarily. I can do the job. Because here I have constants. So I have lambda alpha over gamma of alpha, integral between 0 and plus infinity, x alpha exponential minus lambda x dx. And what is this one? I use the formula in red. I obtain my integral in white from the formula in red if I replace alpha by alpha plus 1. If I replace alpha by alpha plus 1 in this formula, I make exactly appear this term. And so I obtain gamma of alpha plus 1 over lambda to the power alpha plus 1. And now it's finished. I can just simplify. I can simplify the lambda. Lambda to the power alpha divided by lambda to the power alpha plus 1 is just 1 over lambda. And then it remains gamma alpha plus 1 over gamma of alpha. What is this? It's something I have already computed. So let's come back to question 3. The beginning of the question 3. We have seen together that gamma of alpha plus 1 is equal to alpha gamma of alpha. So gamma alpha plus 1 over gamma of alpha is equal to alpha. And so I obtain that the expectation of a gamma of parameter alpha and lambda is just equal to alpha over lambda. Okay? Alpha over lambda. So it's exactly what I want to prove in the question here. And once again, you see that I don't have done computations. Okay? I don't compute. I just say, okay, I know this one from the definition of the gamma density function, and I use what I know in order to compute what I want. Okay? Because I have already done this one previously. I have already justified this one at the beginning of the exercise, so now I can use it. What is more, for the midterm exam, okay, you will know this one. If I ask you to compute this kind of integral, it will be just an application of the definition of the gamma density function. So I have the expectation. If I want the variance, it is sufficient to compute the expectation of x squared. Okay? That's what we are going to do. So I put here the fact that I have computed the expectation of x as lambda or alpha over lambda. Now, are you okay with what I have written here? Because I will erase. Because in fact what I want to do now is exactly the same. I will just have to modify a little the things. If I want the variance is defined as the expectation of x squared minus the square of the expectation of x. So it means that I want to compute this. Okay? So it means that I want to compute this. So it means that I want to compute this. So it means that I want to compute this. Okay? So it means that I want to compute this one. Okay? Now, with alpha plus 2 instead, because I want to make appear x to the power alpha plus 1, so I need to take here alpha plus 2 inside this expression. So I obtain gamma of alpha plus 2 over lambda to the power alpha plus 2. Okay? And I obtain lambda to the power alpha over gamma alpha, gamma alpha plus 2 over lambda alpha plus 2. That is equal to what? So I can simplify the lambda to obtain 1 over lambda square. And I have gamma of alpha plus 2 over gamma of alpha. It is just this last expression that I have to handle. We are going to use once again what we have used previously, that is this one here. I know that gamma of alpha plus 2 is equal to alpha plus 1 gamma of alpha plus 1. Gamma of alpha plus 1 is equal to alpha gamma of alpha. So this one is equal to what? So alpha plus 1 alpha over lambda square, using 2 times this one in order to simplify gamma of alpha plus 2 over gamma of alpha. Okay, so I go quickly because it's exactly the same computation. If you have understood the trick here, that is to use this one, it's finished. So, what I have obtained that the expectation of x is equal to alpha over lambda. I have obtained that the expectation of x squared is equal to alpha plus 1 alpha over lambda squared. If I want to compute the variance of x, it is equal to what? The expectation of x squared, that is alpha plus 1 alpha over lambda squared, minus the square of the expectation, that is minus alpha squared over lambda squared, and I obtain this way, just alpha over lambda squared. That is exactly what I want to obtain here, alpha over lambda squared. Okay. And typically, taking alpha equal to 1 and lambda, I recover that the expectation and the variance of an exponential is 1 over lambda squared. So it means that if you know The formula for the gamma, you will know it for the exponential, so you don't have to know the exponential. In fact, it's just a special case of the gamma. For the chi-square, that is just a gamma of parameter 1/2, the expectation is 1 and the variance is 2. Okay? The expectation is 1 and the variance is 2. So it means that you don't have to know nothing about the chi-square of parameter 1 because it's just a special case of what happened in the case of the gamma. Okay? A priori, uniform Gaussian gamma will be enough to know everything that we have done in class together at this stage. Okay. Do you agree with my computation? Not with my computation, in fact. I don't compute because I don't want to compute. Because when I compute, I do mistakes. So I prefer to use something that I know from the course, to use it several times, and to be sure that at the end I won't do mistakes in my computation. It's what I want you to do. You can compute, it will be long and with mistakes, so you can choose. Okay? As you like. Okay. What I'm using, so before the break I will do this one that is just in fact more definition than something else, and we are going to finish with the exercise 6. And then, okay, I will do the break and then I will continue with the course. That is a very small part, but that is a small but powerful part. It is the one concerning moment generating function. So, do you have some questions concerning my computations here? Okay? So I erase. I will use the trick another time in the exercise 6 here. The same thing. Okay. So exercise 5 once again, and just the question 8. In fact, I have nothing to do in the question 8, but it's more a definition that I consider that it is included in the course typically because it will be a generalization of the definition of the chi-square, something that will appear in the statistical part. Okay? So first, the question starts with a definition. Okay? It's a definition that you can consider as force. Okay? We say that x follows the chi-square of parameter k, with k belonging to n star. Okay, if x follow if x, so be careful between the x here and the key, follows the gamma. So I have already done the job for k equal to 1, okay? For a general k, it's a gamma k over 2 1/2. This one, why not? And typically, for k equal to 1, I recover what I have done in question 6. That is, a gamma 1/2 is just a chi-square of parameter 1. Chi-square of parameter 1 being defined as the square of n01. We will see in the list 6 of exercises that I will do next session, okay, that this chi-square of parameter k has also a link with Gaussian distribution. We have seen here that the chi-square of parameter 1, that is this one, is a gamma 1/2. That is, in this expression, what appears if I take k equal to 1. For a gamma, for a chi-square of parameter k, we will see that in fact it is the distribution of the sum of the square of k independent n01. So you take x1 square plus x2 square plus xk square, where all of them are independent and n01, you obtain this density function. So a chi-square of parameter 1 is just the square of n01. The chi-square of parameter k will be the sum of the square of k independent n01. I will do the job, okay, in a few minutes, next session. Okay? So here, so I have defined this, okay, and the question is stupid from what I have done previously. It is compute the expectation and the variance. I just have to plug inside with the good parameters. Okay, so what is the expectation in this case? The expectation of a chi-square of parameter k, the chi-square of parameter k is just a gamma k over 2 1/2. So the expectation is alpha over lambda, that is k over 2 over 1 over 2. That is the expectation is k. Okay? Because I have a chi-square defined as a gamma, and I have the expectation and the variance of a gamma here. And for the variance of x, I have to take alpha equal to k over 2 in the expression, and divide by lambda square, that is just 1 over 2 square, and I obtain 2k. Okay? Once again, if you know the definition, you don't need to know this one, you just have to know what are the formula for the gamma, and you will recover the one for the chi-square of parameter k. And I repeat that we will see in the list 6 of exercises that this chi-square of parameter k is related with the sum of the square of k independent and 0, 1. Okay? So something that will appear in the statistical form. Okay? Allez, before the break, I want you to do this one. And I will give you the break when one student will find this result. So it can be in 1 minute or tomorrow. But if you have understood what we have done before, it should be 1 minute. Exercise 6. So, it's the exercise 6 of the list 5. So the idea is the following. I have z, that is an exponential of parameter lambda, okay? And I want you to compute the expectation of z to the power n. And I want you to prove that it is equal to n factorial over lambda to the power n, for n belonging to n. Okay? Try to do by yourself. Of course, for n equal to 1, we recover the fact that the exponent and the expectation is 1 over lambda. Of course. give you the solution as promised, okay, because some of you have already found the solution. So just, I write the definition of what I want. That is the expectation of z to the power n. It is what? It is just the integral, so I write it this way last time. This one, okay, where fz is the density of my exponential of parameter lambda, so I obtain the integral between 0 and plus infinity. I can write it this way, lambda z to the power n exponential minus lambda z dz. Okay? And why I have nothing to compute? Because I have already done the job. I have already done the job. You see what I have here. I have a negative exponential and z to the power something. I am able to compute this kind of integral from the definition of a gamma density function. From the definition of a gamma density function, I know that the integral between 0 and plus infinity of x alpha minus 1 exponential minus lambda x dx is equal to gamma of alpha over lambda alpha. So what I need to have here, I want this term. So I have to take by lambda here, no problem, and alpha equal to n plus 1 in the definition here. So I have here gamma of n plus 1 over lambda of n plus 1. Okay. What is gamma of n plus 1? I have done the job in question 3. Gamma of n plus 1 is equal to n factorial. And it's finished. N factorial over lambda to the power n plus 1. So it's the part in red that I integrated, that I obtain this one. If I multiply by lambda, I have exactly what I want. And so I obtain n factorial over lambda to the power n. Okay? And I have here the expectation of z to the power n when z follows an exponential of parameter lambda that I can compute very quickly now from what I know of the gamma density function. Okay? So let's do the break. So let's talk about the moment generating function. Okay, and typically we are going to see several examples in relation with the distribution we have already seen together. Okay. So first of all, the definition. Okay. The moment generating function is just something that is related to computation of expectations. Okay. So it works both in the two cases we have seen together, that are the discrete case, where expectations are sums, and the case where I have density function, where expectations are integrals. Okay? So, let's read the definition. So suppose that x is a discrete random variable, or as a density function, the two cases we have seen together, okay? Then the moment generating function of capital X at the point small t belonging to R, when it exists, and I will do a comment on this one just after, is given by this one. Okay, so it's a mapping. Okay, so don't sleep. It's not that boring, moment generating function. And you will see that it simplifies a lot the computations. So, the moment generating function, so m, of the random variable x at the point t, is given as an expectation. So an expectation that may exist or not, maybe plus infinity sometimes, but when it exists, okay, it is the expectation of exponential of t capital X. So of course I have two cases. The case of discrete random variables and the case of continuous one. Okay, so what are the two formula in the two cases we have seen together. So in the discrete case, what I have to compute, it's the sum from I belonging to capital I, exponential t xi, the probability that x is equal to xi. It is the definition of the expectation in the discrete case. Okay, the xi are the countable number of possible values for capital X. And in the case where x has a density function, this expectation is none other than an integral. It's the integral from minus infinity to plus infinity of exponential tx times the density function of x. Okay? And since you have sums and integrals, so you have sums here and integrals of positive mappings. It's not that bad when you want to compute. It means that you obtain a number or you obtain plus infinity. You don't have the possibility. You have these two possibilities only in this case. Okay. But we will see examples where, okay, but it is not defined everywhere. So this is the definition of the moment generating function of x at the point t when it exists. There is one point where the moment generating function always exists. If you take t equal to 0, in my definition, for t equal to 0, what is mx of 0? It is just the expectation of what exponential of 0 times x, that is in fact expectation of 1, that is equal to 1. Okay, so I know at least one point where the moment generating function is defined for any kind of random variable. Okay? So we are going to try to compute it in some special cases. Okay? So I will do the job today for the Poisson distribution in the discrete case. For the gamma distribution we have previously seen together. With the Gaussian distribution with mean 0 and variance 1, because I will be able to, okay, to deduce what happened for general Gaussian random variable from this one. Okay? Let's do the job for the examples that are on the slide here. Okay? So I want to compute this quantity in the case that are written in the example. Okay, so let's start with the Poisson distribution of parameter lambda. Okay? So if I am a Poisson distribution of parameter lambda, okay, so if x follows the Poisson distribution of parameter lambda, it means that the probability that x is equal to k is equal to exponential minus lambda, lambda the power k over k factorial for all k belonging to n. Okay? It's the definition of a Poisson of parameter lambda. What I want to compute is the expectation of the exponential of t capital X from the definition of the expectation in the discrete case. It will be a sum from k equal to 0 to plus infinity of exponential t k multiplied by the probability that x is equal to k, that is exactly what I write in here. Okay? My question now is how to compute this sum. So it seems to be complicated, but in fact it is not. Why it is not? Because when we have worked with the Poisson distribution, I have said to you that when I work with the Poisson distribution, there is a relation that I have to know. I need to have in mind. That is the definition of the exponential itself, using a sum. Okay? So we have seen together, in order to check that this one was a probability mass function, that expectation of x may be written as a sum from k equal to 0 to plus infinity xk over k factorial. Okay? But the idea is to use what you have in red in order to obtain what I want. So I have the exponential minus lambda that I can remove if I want, okay, because it doesn't depend on k. And then I have a sum from k equal to 0 to plus infinity. And if it's possible to put it on this form, it would be perfect because it would be possible for me to express it as an exponential. Is it possible to do? I have the over k factorial for sure. Okay, here. And then, if I want to express this one on the form x to the power k over k factorial, which x I have to take? Lambda is not enough because I will have this term also. X to the power k
plus x to the power t.
I don't have x. I have something to the power t if you want, but it's not. I have to do the sum with respect to the power. Okay, so t is fixed and k is moving. Lambda times exponential t to the power k. I obtain lambda k and exponential t to the power k. It's what you have said? No? So it's what I have understood. Okay, so exponential t to the power k, that is just exponential tk by the properties of the exponential. And now it's finished. Now it's finished because I obtain what? I continue here. I have my exponential minus lambda before here. And then I have what? I replace x by lambda exponential t, and I obtain exponential of lambda exponential t. Okay? I can regroup the terms a little, and I obtain what? Exponential lambda of exponential t minus 1. I can write it this way. Okay? So I have here the moment generating function of a Poisson of parameter lambda that I am able to compute for any t, and that is a number for any t because of this one and because of the fact that this relation is true for all x belonging to R. I have no condition on x in order to make this equality okay. Okay, so the moment generating function of a Poisson is this one. Do you agree? Nothing new, huh? I just use a trick that we have already used in the definition of the Poisson itself. Okay, so I have this. So let's remark one thing. If I compute the derivative of the moment generating function, what I obtain? So it is of the form exponential of u. So it is u prime times exponential u. What is u prime? U prime is lambda exponential t. Okay, so if I compute the derivative of this one, I obtain lambda exponential t, okay, multiplied by exponential lambda exponential t minus 1. Okay? Why not? U prime times exponential u. Okay? What I obtain, if I take the value of this derivative at 0, lambda. And what is lambda? For a Poisson of parameter lambda, I can see it as the exponential. the expectation. Let's continue with my little computation, why not? So may I erase this? Once again, for Poisson, have this in mind. Okay? For Poisson, have this in mind. So may I erase and repeat? Yeah? If I compute the second derivative, and after I will stop, okay, but it should be possible to continue. The second derivative is just the first derivative of the derivative, so I have to compute the derivative of this one. It is of the form u times v, so u prime v plus uv prime with the v that is of the form exponential of some one, okay? So I can compute the derivative, that is u prime, that is lambda exponential t u prime v, that is exponential lambda exponential t minus 1 plus u and v prime that I have already computed here, that is lambda exponential t exponential lambda exponential t minus 1. Why not? It's just a computation, basic one, computation of derivatives. What I obtain for t equal to 0. What I obtain for t equal to 0. But the first is lambda plus lambda square. What is this one? No. No. Not the variance. What is the variance of a Poisson of parameter lambda? Lambda square. Lambda square? No. I have everything. Lambda, lambda square, 1 over lambda, lambda square. Okay. Pi. So it's lambda as well, okay? So here you have just in fact the expectation of x squared. That is the variance plus the square of the expectation. The variance plus the square of the expectation, that is the expectation of x. So what I have done this little computation? I have done this little computation because this mapping has a name. Moment generating function. What are the moment of a random variable? What we call the moment of the random variable, okay, is the generalization of the expectation, expectation of the square, and so on. So the moments are expectation of x squared, expectation of x to the power 3, expectation of x to the power 4, and so on. And you see that the link between expectation and expectation of x squared is not that complicated for this mapping. Okay, if I compute the derivatives, in fact, from what I know, I remark here that I obtain expectation of x here, expectation of x squared. So it's not that surprising because it's a general result we are going to see just after, but okay, so it means that instead of computing, once I have computed the moment generating function, to compute expectation, I just have to compute derivative. Okay? So you see what may be the interest of such a mapping. Because instead of computing integrals, you will have to compute derivative. Okay? For all expectation of x, expectation of x squared, expectation of x to the power 3, and so on. So I remark this. So what you have to know, what is the moment generating function for a Poisson? For the moment, that's all. And be able to compute derivative. Okay? So I continue. I continue with the gamma we have previously studied. Okay? So I erase what I have done. Okay? And we are going to see what happened for the gamma. Once again, for the gamma, we will have to do nothing. So let's come back to the definition of the gamma we have seen together. That was this one here. Density of a gamma. if I suppose that x follows the gamma of parameter alpha lambda, if I am interested in the moment generating function of x here, I am in the situation where I have a density function, so this moment generating function will be expressed as an integral. Okay? The density function is given by the top of the slide here. So I obtain integral between 0 and plus infinity of exponential tx, okay, lambda to the power alpha, x alpha minus 1, exponential minus lambda x dx over gamma of alpha. Okay? I have this. Why not? My question is how to compute. What can I do? What can I do in order to compute? In order to compute, keep in mind that you know that all these integrals are equal to 1. For any alpha, any lambda. It means that if I have something of the form x to the power some 1 and a negative exponential, you will be able to compute the integral function. Here I have two exponentials. First I can regroup them in order to see what happens. Okay? So I can write the thing this way. Lambda alpha over gamma of alpha, let's say. Integral between 0 and plus infinity. X alpha minus 1. And exponential minus what? Lambda minus t x dx. Okay? I have just regrouped the two exponential in one exponential. But what I know things from what we have done in the exercise 5. We have seen together that the integral between 0 and plus infinity of x alpha minus 1 exponential minus lambda x dx, this one is equal to gamma of alpha over lambda of alpha, but I have a condition to make this integral well defined. The condition is that alpha is strictly positive and lambda is strictly positive. It's the way I have defined the density function. Okay, I have condition on alpha and lambda here that are lambda positive, alpha positive. But I have something of the same form here. The only thing that is changing is that I replace my lambda by lambda minus t. Okay? So if I want to continue my computation, I need to impose one restriction on the parameter. Because this integral is not always finite. It is finite when the parameter here is strictly positive and when the parameter here is strictly positive. Okay? According to what I have written here. So this one will be finite. That is, the moment generating function will be well defined if these coefficients here is strictly positive. That is, if t strictly less than lambda. If t is not strictly less than lambda, you obtain an integral that is plus infinity. Okay. So if t is strictly less than lambda, I obtain what? By replace by what I know. So it is lambda to the power alpha over gamma alpha, and I have to multiply by what? Gamma of alpha divided by lambda to the new, the new lambda, that is lambda minus t to the power alpha. And I obtain at the end, okay, something that I can write this way, lambda over lambda minus t to the power alpha. Just one remark. Don't forget that a moment generating function, when it exists, is a strictly positive number because it is the expectation of an exponential. So here, if you don't impose the condition lambda strictly greater than t, you may obtain something that is negative here. Okay, so it's important to have this condition in mind. First, because it's not well defined, and of course, you obtain something that is meaningless. Okay? I have this. What I use, once again, in order to compute this integral and to see where is it well defined, I use what I know from the gamma distribution. Okay? And I just replace here alpha by alpha, it's the same, and lambda by the new lambda, that is lambda minus t. I plug it inside here, and I obtain exactly this term. And I obtain this one. So you have the moment generating function of a gamma here. So if gamma, if x follows the gamma alpha lambda, the moment generating function of x is equal to lambda over lambda minus t to the power alpha if I have this condition. And it is not defined otherwise because the expectation is not finite otherwise. Okay, why not? And I see that once again I don't compute, I just use what I know. Okay? Now I erase this. One remark also, if you put t equal to 0, you still obtain 1. Don't forget this. Huh? If you obtain a formula and if you plug t equal to 0 inside and you don't obtain 1, it means that you have a problem. Okay, because this is always equal to 1 at 0. Okay? Are you okay with this computation and with this condition? This condition is in order to make sure that this integral is a finite number, not equal to plus infinity. Okay. If I compute the derivative of this expression, what I obtain? How to compute the derivative of this one? It's not that classical expression, but I can express it this way. I can express it as an exponential of alpha logarithm of lambda minus the logarithm of lambda minus t. The logarithm of the difference between logarithm is the logarithm of the ratio. Alpha times logarithm is the logarithm of what I have inside to the power alpha, and exponential of logarithm is equal to identity. Okay, so I obtain this expression. So if you are not able to compute directly the derivative of this one, you can use this expression where you will just have to compute the derivative of exponential and logarithm. Okay. So if I compute the derivative, what I obtain? I have something of the form exponential of u. What is u prime here? But it's the derivative of this one. So here I have constant at one moment, and I have the logarithm of a mapping. Okay, the derivative of the logarithm of a mapping is f prime over f. So here it's very basic because it's a linear mapping here, and I obtain at the end 1 over lambda minus t. That is the derivative of what I have. I have forgotten the alpha here, so it is this one. Alpha over lambda minus t, it's the derivative of this one. Okay? Multiplied by the exponential of the same thing. Lambda minus t. Okay. If I take the value at 0, what I obtain? What I obtain? This one, that is just, once again, the expectation of x. Okay? So it should be possible to compute the second derivative. I won't do the job, but you can do it. If you compute the second derivative and take the value at 0, you will obtain the expectation of x squared. That is the variance plus the square of the expectation. Okay? But here, when I compute only the third derivative, I remark that I recover the expectation of x when I take the derivative of the moment generating function at 0. Okay? Okay. So this is the moment generating function of a gamma of parameter alpha lambda. If I want to compute the derivative, I just keep in mind that I can express it as an exponential, in fact. Okay. In order, for example, to compute its derivative and remark that the derivative at 0 is just the expectation of my random variable. I have this. Last example. So, I have done the job for a gamma. According to what I have done in the exercise 5, I know that an exponential of parameter lambda is just a particular case of a gamma. Exponential of parameter lambda is just gamma 1 lambda. Okay? You have seen this in the list 5. So typically, for an exponential of parameter lambda, the moment generating function t is equal to what? I just have to replace alpha by 1 and lambda by lambda. So it is lambda over lambda minus t. Okay, for t less than lambda. You have here the moment generating function of an exponential of parameter lambda. Okay? In the exercise 5 of the list 5, we have also seen that the p square of parameter k is just, by definition, a gamma k over 2 1/2. Okay? So if I want the moment generating function in this case, and from the previous computation, I have alpha that is equal to k over 2. I have lambda that is 1/2. It is true for t less than 1/2. And I can simplify a little. And I just obtain 1 over 1 minus 2t to the power k over 2 for t less than 1/2. You have here the moment generating function of a t square of parameter k. Just plugging inside the good parameters. Okay. It means that you have only to know this one. If you know this one and are able to know the links between exponential gamma, chi square and gamma, you have the moment generating function of the two others. Okay? This. And the last computation I will do at this stage will be the one of n01. Okay, the moment generating function of n01. And if you have one moment generating function to know in your life, it is the one of the n01. we'll use it a lot. So in probability and in statistics for sure, but also in finance. Okay. Maybe you have heard about the Black and Scholes models and the price of a contingent claim in these kind of models, okay, may be computed, not that completely. And the idea is to use the moment generating function of the Gaussian to obtain the nice formulines. Okay. So are you okay with what I have done here? So let's do the same for the Gaussian, N01. So I erase things here. So for N01, so at this stage, computing moment generating function is just little exercises concerning integrals, once again, or sums. Okay, so in this situation, the moment generating function is given by the integral minus infinity plus infinity exponential tx, and I have to multiply by the density function of N01. Okay? 1 over the square root of 2 pi exponential minus x squared over 2 x. Okay? So first of all, I can see that here the moment generating function will be defined for any t. I have no conditions on t because, okay, here, okay, I have an exponential. Okay, but here I have a negative exponential with x squared, while here I have only t. So the winner in plus and minus infinity is this one. Okay. So how to do? It's a kind of computation we have already done together. So my Gaussian is here. I am able to compute the integral of all these ones here, knowing that this integral is 1. Okay? But once again, I see that I have something involving the density of N01. I have an extra term here. And if I want to come back to what I have in my slide, I have to make appear a perfect square. So computation I have already done. Make appear a perfect square in x here. So I have my x squared over 2. Okay, so let's write it this way. I have my minus x squared over 2 plus tx. And the idea is to express it as minus 1 over 2 square, okay, plus something that is just a function of t, that is independent of x, if it's possible. Because if I do this, when I will compute the integral of the exponential of this one, I will have to compute the integral of the exponential of this one that I will be able to do using this formula. So how to do? But I don't have the choice. Okay. I put minus 1/2 into factor. What will be? So I need to make appear the x here. So I put an x inside here. I will have my square. And if I want to make appear the tx, okay, what I have to do? I have to put minus t here. If I put minus t, the double product will be minus 2tx divided by 2, so minus tx with a minus plus tx. But if I do this, I have an extra term, that is the one coming from the square of this part here. So I have to take minus t squared over 2. So I make appear a perfect square in x plus an extra term that will be independent of x. And now very easy to compute my integral.
So it should be plus t squared over 2 because, yeah.
I have a minus
Yeah,
here.
minus,
So I have a plus. You're right. Okay, huh? Minus t squared is t squared, so I have minus t squared over 2. If I want to erase it because it doesn't appear in my initial expression, I have to put a plus. Okay, now it's finished. Why it's finished? Because if I come back to the integral I want to compute, that is the moment generating function of my n01. How to express it? I will express it this way. So it's exponential t squared over 2. Okay, multiply by the integral minus infinity plus infinity of exponential minus 1 half x minus t squared over the square root of 2 pi dx. What is this? What is the integral? What is this integral? 1. Because you take, in the blue formula in the slides here, m equal to t and sigma square equal to 1. Okay? So the integral of a Gaussian density is 1. So I have this nice expression for the moment generating function of n01. Exponential t squared over 2. Okay? Exponential t squared over 2. If I compute its derivative, once again I have exponential of u. So it's u prime, that is t, exponential t squared over 2. If I take mx prime at 0, I obtain if I take t equal to 0, I obtain 0. That is the expectation of my n01. That has an expectation equal to 0. If I compute the second derivative, so I have a product here, u prime v plus uv prime. And if I compute the second derivative at 0, I obtain what? One. That is the expectation of the square of my n01, because in this case the expectation of the square, when I have an expectation equal to 0, is just a variance. Okay, so I have done these classical computations that are not that difficult. Okay, I have it for the Poisson, I have it for the gamma, so for the exponential and the chi square, and I have it for the n01 for the moment. Okay. Just things that I can do from the definition. Okay. So are you okay? So it's just, once again, computations of integrals of sum. In fact, nothing to do with probability at this stage, except for the definition with an expectation here. Okay. So what will be some tricks concerning this moment generating function? Okay. And its use. So two important things. So it's a really strong result. Probably for the moment the strongest result we have seen together. And as it is strong, okay, as you can imagine, it is not that easy to prove. Okay, really difficult. In particular, the first point. It is really difficult, and that's why even you don't have the proof in the list of proof. Okay? So if you want some reference I will be able to give you concerning this proof, but it's totally out of the scope of the program of this course. But what you need to know, we have seen together that if I want to characterize the distribution of a random variable, I have some tools. In the discrete case, I have the probability mass function. In the case with density, I have the density function. But I have other tools. I have also said that the distribution function in both cases characterize the distribution of a random variable. Okay? In the case of the moment generating function, it's the same. What is the statement? So, I have two random variables. Okay? I have said previously that it's not necessary that the moment generating function is defined everywhere. But suppose that it is defined around 0. At 0, I know that it is defined because the value at 0 is 1. But suppose that there exists a little set around 0, here, in fact, a little interval around 0, in such a way that the moment generating function is well defined. If I come back to my examples, here I have seen that in the case of the Poisson, in fact, for this interval, I can take by everybody, the whole R. For the Gaussian, I can also take the whole R because the moment generating function in this case is defined everywhere. But typically, in the case of the gamma, I need to impose that T is strictly less than lambda. Okay, so T is strictly less than lambda means that I am defined around a little interval around 0. So suppose that you have two random variables such that their moment generating function are defined around 0, let's say. If the moment generating function coincide, then they have the same distribution. Here, it's the notation for the distribution function. So if they have the same moment generating function around 0, then they will have the same distribution function and so the same distribution. Okay? So it means that you have now a new tool in order to prove that two random variables, or in order to prove that, for example, if I ask you to prove that x follows the n01, okay, you can prove that its density is given by 1 over the square root of 2 pi and so on, or you can also prove that its moment generating function is given by this one. Okay? If you have a random variable with this moment generating function, you are sure that you have n01. Okay? So the moment generating function characterizes the distribution of a random variable. Okay? So a really powerful result here. So, no words about the proof, but the only thing I can say is that when I have the definition of the moment generating function here, I have inside exponential mappings. Okay? And the only thing that I will say that is a very, let's say, not rigorous, is that with exponential, okay, I can do a lot of things. In the sense that with exponentials, I can approximate, taking linear combination of exponentials, I can approximate, in fact, any type of continuous mapping. Which means that when I have a result concerning the exponential, the expectation of exponential, in fact, I have the result concerning the expectation of everybody as a function of capital X. This is the intuition below this result here. Okay? Exponential mappings, okay, allow me to build, okay, in fact, all the continuous one. It's not that easy to do and to prove, okay, but it's the idea. So, but what I want you to keep in mind is that if you have two random variables with the same moment generating function defined around 0, they have the same distribution. Okay? So I repeat that if I want you to prove, for example, that you have something that follows a gamma, you can prove me that its moment generating function is the one of a gamma. Okay? The one of a gamma that is in the course because I have done the computation previously. Okay? And in a lot of situations, okay, it is easier to work with the moment generating function than to work with density or probability mass function or distribution function directly. Second result in the proposition 20, so it's something that I have already remarked. but I need some conditions that are fulfilled in what I have done here to justify what can I do. I said the following, so if you start from the moment generating function, okay, if you are able to compute its derivatives at 0, then the derivative at 0 are related with the moment of the distribution. Typically, the first derivative is the expectation, the second derivative at 0 is the expectation of the square, the expectation of x cubed is equal to the third derivative at 0, and so on. And to be sure that I am differentiable, I just need to impose that the moment exists, in fact. So if the expectation exists, the moment generating function is differentiable at 0, and its derivative give me the expectation. If the expectation of x squared is finite, then the moment generating function at 0 is twice differentiable, and in order to compute it explicitly, I just have to compute the second derivative at 0, and so on. Okay? Here, it's not that complicated, because it's a so-called theorem, okay, in probability theory. And I just want you to show you what is this, okay, quickly. In fact, I have to come back to the definition of the moment generating function. The moment generating function at the point t is this one. Okay? Suppose that you are able to do what you want. Okay? And there is a result, okay? Or result, a set of results that are called Lebesgue theorem, but I won't enter into details because it's not my purpose in this course, but just say that I have expectations here depending on a parameter, t. It's a real parameter. Okay? And suppose that I want to compute derivatives. Okay? I want to compute derivatives. So keep in mind that for me, an expectation is just an infinite sum or an integral, let's say. Okay? So it's the derivative of the expectation. And what would be a nice property concerning the derivative of my expectation here? If you want to compute the derivative of such a thing here, what I may expect. Keep in mind that the expectation is linear. Okay? And you know that if you have a linear combination, let's say, the derivative of the linear combination is the linear combination of the derivatives. So I have to work a little if I want to extend it to an expectation, but an expectation as a sum or as an integral is linear. Okay? And in fact, derivative of an expectation of the derivative, it should be a nice result to have. But if I do this, so if I suppose that I am able to invert between the expectation and the derivative, and I have results to do so, okay, but that are not in the scope of this course. But then, if the derivative of my expectation is just the expectation of the derivative, it's very easy to compute the derivative of this one in t. What is the derivative of this one in t? X exponential tx. Okay? I compute the derivative with respect to the variable t. Okay? And what happened at 0? And this is the intuitive proof of this kind of result. My only problem, if I do this, is just a technical problem. That is, why I have the right to invert between the derivative outside the expectation and the derivative inside. I have some results that allow me to do this. Okay? But it's not points on which I want to spend time in this course. Okay? So just keep in mind that if I have the right to do what I want, computing derivative, so I can continue on. If I compute the second derivative, what happens? I have to compute the derivative of this new expectation. So I compute the derivative of what I have inside, and I will obtain expectation of x squared exponential tx. If I take t equal to 0, I have expectation of x squared, and so on. Okay? So this one is not that complicated to obtain, because it's just to justify that I can invert between expectation and derivative. Okay? In this course, I will suppose that it is always possible, because we will always be in the good condition in order to do this. Okay? But a priori, you will never have to do this, okay? Typically in an exam. Okay? It was just to justify this proposition. So what I want you to keep in mind with moment generating function is that moment generating function characterizes the distribution. And then, if I compute the successive derivative of the moment generating function at 0, I recover the moments of my distribution that are expectation of x squared, and so on. Okay? Okay? So, it's a computation I have already done, but when I say moments of gamma distribution revisited, it's just that I have previously computed the moment generating function of a gamma. If you want its expectation, compute the derivative and take the value at 0, and you will obtain, as I have already done, alpha over lambda. You want the expectation of x squared, compute the second derivative and take the value at time t equal to 0. You will obtain the expectation of x squared, that is alpha over lambda square plus alpha over lambda, okay, and so on. Okay. So the moment generating function is a great tool in probability theory in order to characterize a distribution that is often more flexible than the density of the distribution function, and that is also a powerful tool in order to compute the expectation of the moments of the power of a random variable. It's what I want you to keep in mind in this point. Okay? So these two. Questions? So if you are really interested in the proof, I would give you references, but it's a proof that deals with analysis, okay? Nothing to do, in fact, with probability. Okay? So that's why I don't spend time on it. So this one are easier and easier, but also very important. Okay, so quarter. Okay, what is the meaning of the two statements? Second statement first. If I have two random variables that are independent, the moment generating function of the sum is the product of the moment generating function. Okay? First statement, if you linearly transform a random variable, it is very simple to obtain from the moment generating function of the variable the moment generating function of the linear transform. The proof is very short in both cases. Okay? So let's do it. So suppose that you start, okay, with x, a random variable, and suppose that you know mx. Okay? So you know mx, that is given by the expectation of exponential tx. I know where it is well defined, I am able to compute, I know everything. Okay? And suppose now that you are interested not in the moment generating function of x, but in the moment generating function of a plus bx. Okay? You linearly transform x. It's a linear transform of my initial random variable. If I come back to the definition, what is this? It's exponential t, so if I want it at the point t, exponential of t times what? By a plus bx. At the end, I obtain what? the expectation of exponential at times exponential tbx. This one is a constant that I can remove from the expectation because it's not a random variable, it's a constant. And it remains the expectation of exponential tbx. But what is this one? It is just the same kind of expectation as the previous one, just I replace t by tb. So I obtain exponential at, the moment generating function of x at the point where bt or tb is the same. I just use the fact that the exponential has some particular property, and that, okay, I have an expectation to compute of the exponential of a linear transform of x. So if I read the statement, what I have, I said that, okay, I have this one, but if I want to have this one, I need that the moment generating function of x is well defined at this point here, because I want to be able to write. It's exactly the meaning of what I have done. Here I have supposed that I am able to do all the computations. If I want to be able to do them, okay, concretely, I need to suppose that this one is well defined in order to make this one well defined. Okay. So if I have a linear transform of an initial random variable, then I am able to compute, in most of cases, the moment generating function of a linear transform. Okay? And even here it's more than linear, it's an affine transform of a random variable. What may be the use of this one? By the use of this one, maybe if I come back to the Gaussian distribution, I know that if x follows the nm sigma square, okay, I can write it the following way. Something we have seen together. So nm sigma square may be expressed as an affine transform of a n01. Affine transform of a n01. So applying my result here. Here it's nice because I know that the moment generating function of y is defined everywhere. I have no condition on where it is well defined. It is well defined everywhere. So if I use the proposition, statement 1, the moment generating function of x at the point t is what? Will be exponential mt time the moment generating function of y at the point sigma t. And what is the moment generating function of y at the point x? It's exponential x squared over 2. It's just the previous computation we have done together. I know the moment generating function of y, that is exponential x squared over 2. Okay? So I just have to plug inside, and I obtain, for this one, exponential mt, exponential sigma squared t squared over 2. You have here the moment generating function of nm sigma squared that can be deduced easily from the moment generating function of n01. It's an expression that you have to know. Moment generating function of nm sigma squared that I recover basically. So if you know the one of n01, with one line you are able to recover the one of nm sigma squared. That is exactly this one. Okay? So if I linearly transform or affinely transform a random variable, in general it is possible to recover the new moment generating function from the old one, the one of the initial random variable I have transformed. Okay? And the last result in order to conclude today, once again, that will be very, very basic to prove, one line, but with great consequences, the fact that if I have two random variables that are independent, it's very easy for me to compute the moment generating function of the sum from the moment generating function of x1 and the moment generating function of x2. So let's do the proof of this one. So do you have some question on what I have done here? Nothing to do, just basic properties of expectation here that allow me to do the computation in the case of n sigma squared. So for the small 2 here, suppose that x1 and x2 are independent. If I am interested in the moment generating function of x1 plus x2 at the point t, by definition, it is the expectation of exponential t x1 plus x2. Okay? By definition of the moment generating function. But from the property of the exponential, I can write this one as exponential t x1 times exponential t x2. And from the fact that x1 and x2 are independent, the expectation of the product will be the product of the expectations. Because if x1 and x2 are independent, any function of x1 is independent of any function of x2. Here, the exponentials. So by independence here, then I have expectation of exponential tx1, expectation of exponential tx2, and I have just by definition m x1 of t times m x2 of t. It's just a basic consequence of independence. Okay? A basic consequence of independence. So let me show you one example, and after I will continue next session. Okay? We have almost finished with the moment generating function, so it's not that huge for the midterm. Okay? And you will see that it will help you a lot to know this. So you have this proof, okay, and let's see a little example. This second statement will allow us to obtain in a very efficient way what is the distribution of the sum of two independent random variables in particular situations. So typically, suppose something that we have already done together, that is the following. So suppose that you have x1 that follows the Poisson of parameter lambda 1. Suppose that x2 follows the Poisson of parameter lambda 2. And suppose that x1 and x2 are independent. Okay? What we have already proved together. What we have proved together already in the list 3 or 4, I don't remind. What is the distribution of x1 plus x2? Ooh. Exercise 3 here. I have done the job with you. The idea was to compute the probability mass function of the sum. And in order to do this, okay, we have used the Newton formula a plus b to the power n is equal to and so on. So I need to do computation if I want to do the job. What happened now? In order to recover exactly the same result. But from the previous proposition, I know that the moment generating function of the sum is just the product of the moment generating functions. If I know what is the moment generating function of a Poisson, it's something that I have done just after the break. What I obtained. What is the formula I have obtained for the moment generating function of a Poisson? Exponential lambda of lambda t exponential t minus 1. So I have done the computation of each of them here, just after the definition of the moment generating function, and I obtain exponential lambda 1, exponential t minus 1, it's for the first, and I multiply by exponential lambda 2, exponential t minus 1. It's the moment generating function of x1 and the moment generating function of x2 I have previously computed. Now what can I do? I can regroup the term here in order to obtain this one. I finish. Because what I recover here, I see that the moment generating function of the soup is the moment, is this one. And what is this one? It's the moment generating function of a Poisson of parameter lambda 1 plus lambda 2. So in one line, I have done the job that was possible to do, but with more and more computations. Here, I just need to know my course. Okay, the fact that the moment generating function of the sum of independent is the product of the moment generating function, and the fact that I know the moment generating function of a Poisson, and that this moment generating function characterizes perfectly the distribution of a random variable. Okay. So next session we are going to do exercise concerning the moment generating function, and the last exercise and the last statement we are going to see together is the following: is that okay, the moment generating function allow me to compute the moments, allow me to characterize the distribution. If I have independence, they allow me to compute the moment generating function of the sum, with this nice trick here. I have a last thing that tells me that in fact, with moment generating function, I am also able to characterize independence. Okay? I am also able to characterize independence. I will define next session the moment generating function of a pair. If the moment generating function of a pair is the product of the moment generating function of each component, then I will have independence. So we will have a powerful tool in order to prove independence through the moment generating function. Okay? And just to tell you, just after you, I have a class of stochastic calculus, okay, where we are going to speak about, but today I will be alone. I will just record my video without students, okay, but I will speak about Brownian motion. Okay, and I will use a lot these tools. The fact that the moment generating function of a Gaussian is given by the expression we have seen together. The fact that if I want to prove independence, the moment generating function of a pair has to be equal to, and so on. So it's things that are used a lot, even okay, in the framework of mathematical theories. Okay. So see you next session.